Let us move on to the next application, the second application for what do you call the Gauss law applications. Okay, so the first one we did in the previous video was spherical shell. Okay, you have already seen through in your previous video. You can have a look first. If you understand that video, then this particular video will be clear. Okay, now for the second one, for the second one, we are going to start for a long straight wire, long straight charged wire. Okay, another important asked previously clear question. For this, what do we do is we take a straight long charged wire which is uniformly charged with say Q. Okay, I need to find electric field due to this long straight wire at some point say P. Okay, so how do we do this, which is at a distance small r. Okay, so again this time we take, you see how we judge about taking the Gaussian surface. That is important. Last time it was a sphere, so we took a sphere so that it becomes easy, similar to the object. This time it's a wire. When you do a cut section, what happens? You get a cylinder. So this time we are going to consider a cylinder. Okay, so how do we consider a cylinder? We consider a Gaussian surface in the form of a cylinder like this. Okay, of length L. Okay, length, you may ask, sir, how can we take, what we are talking is a long straight charge wire, infinitely long. So even though अगर वायर इन्फाइनाइट होगा भी, तब भी लेंथ का मायने नहीं रखेगा. इन द फाइनल एक्सप्रेशन लेंथ विल नॉट बी देयर. That you will see as we move forward. Okay, so how to go on with this particular derivation? First you will write the initial explanation. I'll just dictate the initial explanation like I always do. Consider a infinitely long straight charged wire of let us say charge Q. Okay, after that we will write consider point P at a distance r where electric field must be found. This will be your initial explanation of the diagram. After these two lines, you will be telling, consider a Gaussian surface in the form of a cylinder of length L and radius small r placed on the wire, placed on the long straight wire. This will finish about the Gaussian surface. So this much is done. After that we used to take a small area, write ds vector, correct? So let us do the same thing. I'll take a small area over here and I'll mark ds vector. Okay, electric field vector will also be like this only here, but for the lower face, when I take a small area over here, ds vector will be outside. Okay, electric field will be as it is due to the charges. Upper face also, when I take ds vector will be upwards, electric field will be this way. Okay, so this will be the figure. Now before going forward, one may ask, how are we going to take the ds vector? The area vector, if you have understood about it, whenever you take a small area out of a big area, always we consider a area vector outwards. Okay, that is the way of taking the area vector. So here also what we have done, we have taken for the first case a small area. Okay, and for that small area we have marked ds. सेकेंड वे, दिस सेकेंड पार्ट ऑफ द फिगर, नीचे का सर्कल जो है उसमें भी हमने एक स्मॉल एरिया लिया, यहाँ पर दिखाई दे रहा है, एंड ds वेक्टर नीचे को आ रहा है. इलेक्ट्रिक फील्ड एज इट इज़ विल कम टू द राइट, बिकॉज सारे कंटिन्यूस चार्जेस अगर ऐसे होंगे तो इलेक्ट्रिक फील्ड हर जगह ऐसे ही होगी, टू द राइट होगी, जनरेट. तो चाहे वो इधर का पॉइंट हो या ऊपर का हो या नीचे का हो, इलेक्ट्रिक फील्ड will always be the same direction, isn't it? Okay, area vector above what we have taken also will be upwards. Okay, with this basic, so basically in our cylinder that we have taken, in our cylinder we have three faces now. One is the curved surface. Okay, we can mark that as 1. 2 is the circular surface which is downwards. 3 is the circular top view, top में जो circular face है. So I will consider this, let us say the curved surface as 1, the second surface bottom one, third surface as the top one. Okay, so now इनिशियल एक्सप्लेनेशन ऑलरेडी लिख लिए थे. आई होप यू हैव अंडरस्टूड इट. Let me reiterate once more so that you get a clarity. You need not write all this in your exam. Only this part what I am explaining, only this part is what you write. Okay. So the initial explanation, as I have already told na, consider a long infinitely charged wire with, let us say, charge q. Let point p be at a distance small r from the wire where the electric field must be found. Okay. After taking that, we wrote, consider a Gaussian surface in the form of a cylinder of length L and radius small r. After that, consider a small area element ds, okay, on at point P. Okay. After this, we write again as usual the same way that we usually write. We will write here, from definition of electric flux, we write electric flux is equal to integral E dot ds. Okay. After writing the definition, obviously there are three parts here. So we'll write the cylinder. The cylinder is divided into three parts as shown above. Okay, that will clear. So what happens to our equation? Our equation now becomes, just a minute, yeah, now the page has been, another page has come. So here I can write our equation, the definition, the equation which we just told above now becomes integral 3 times integral e dot ds plus integral e dot ds plus integral e dot ds. Okay, for the first part, for the second part, and for the third part. Okay. Now just get back to the figure. First part is the curved surface. Ds and E are in the same line. If you can see here, ds and E are in the same line. Theta here is 0. But for the second part, E is like this, ds is like this, theta here is 90. Here also E is like this, ds is like this, theta here is 90. So for the second case and the third case, theta is 90. For the first case, theta is 0. So I can clearly write here integral first one E ds will remain as it is. Okay. Whereas I can write it in bracket, integral for the second EDS and integral for the third EDS will be 0. Why? Because theta is 90 for second and third. Okay. So for the first one, theta is 0 for this one. So clearly the flux equation what I got is integral EDS, cyclic integral EDS. Again E comes outside as it is, ds remains. So here now I'll mention what is ds. Integral ds is nothing but surface area of, curved surface area of the cylinder. Yes, surface area of cylinder, to be honest, curved surface area of cylinder, that is equal to 2 pi rl. 2 pi rl. So our equation becomes electric flux is equal to E into 2 pi rl. This is our first equation. Okay. Similarly, we had done like last time, from Gauss law I can write electric flux is equal to 1 by epsilon naught times net charge enclosed is q. Here we put a new thing, but lambda is equal to q by L implies q is equal to lambda L. What is lambda? I hope you know. Lambda is nothing but linear charge density given by charge per unit length. This formula, standard formula. So we can substitute this above. You will get electric flux is equal to lambda L by epsilon naught. This will be your second equation. So now again, as it is, from 1 and 2, what is happening? First equation what we had got was E into 2 pi RL. So E into 2 pi RL is equal to lambda L by epsilon naught. L and L get cancelled. I hope you remember in the starting of derivation I told L ka farak nahi padta. You can see clearly it is cancelling out. Okay. So once it cancels out, rearranging, you get E is equal to lambda by 2 pi epsilon naught r. This will be the equation for this particular case for an infinitely long charged wire. Okay, so just go through. I hope I am always trying to make each derivation of yours in a span of 10 minutes. Last one was a 15-minute video because some basics were taught. So after watching that, you watch this. Before without watching spear, don't come to long straight wire. Okay, now let me revise. Quick revision of what and all we have done. Consider a infinitely long straight charged wire of say charge q, and you can mention there itself, and also let lambda be the linear charge density. That can be done. After that, we will write consider point p at a distance small r where electric field need to be found. After that, consider a Gaussian surface in the form of a cylinder of radius r and length l. That finishes the figure. Consider small area ds at point p. Itna ho gaya. After that, from the definition of electric flux, I am here. From the definition of electric flux, we did as it is. We wrote the definition, then we told the cylinder is divided into 3 parts as shown above. So 3 बार same line लिख लिया. उसके बाद we went forward. Yes, you can see clearly. After writing the 3 parts, I told only 1 part is there. बाकी 2 parts 0 हो जाएंगे because theta will be 90. इसका theta 0 है. Yes, इतना लिखने के बाद ई डी एस आ गया. ई बाहर निकाला, डी एस को कर्व्ड सरफेस एरिया ऑफ सिलेंडर बोला. देन E into 2 pi RL first equation. From Gauss law, the next equation, Gauss law mention किया, Q को replace किया as lambda L from here. After that, we just substituted that here. 1 and 2 equation को लिया, first equation, second equation equate किया, L cancel किया, तो rearrange किया, मिला E is equal to lambda by 2 pi epsilon naught R. So I hope this particular derivation is clear for everyone. Just go through right from the start. Okay, and there is one more, the third equation, the third derivation of Gauss law for a thin plane sheet, that needs to be done. Okay, that we shall see in the next video. Okay, thank you.